Hello everyone, welcome to the lecture series on computer architecture and organization. This is our fourth lecture under unit 4, and in this lecture we are going to see about what are all the communication methodologies we are following nowadays. So these are all the communication methodologies. There are three methods for managing input and output. They are the programmed I/O, also known as the polling, and interrupt-driven I/O, and direct memory access. So the communication methodologies are done between, that is the CPU, between the secondary storage as well as between the main memory, and the CPU communication methodologies will also be done with the I/O devices. So this is the operation for the programmed I/O. The CPU first checks the status of the disk by reading a special register that can be accessed in the memory space, or by issuing a special I/O instruction if this is how the architecture implements I/O. If the disk is not ready to be read or written, then the process loops back and checks the status continuously until the disk is ready. This is referred to as a busy wait. So this is a busy wait terminology, and this para says how the polling of this CPU is also being done. So now if you see this process, first it enters, that is, it checks the status of the disk. Next, it checks whether the disk is ready or not. So if it is not ready, then what happens in the sense, it again go back and keeps on disturbing the disk whether it is ready for not. Then if it is yes, then it sends the data from the memory to disk when writing, or from the disk to memory when reading. So when it is done, it finished, it checks for whether it has finished or not. So if it is finished, if it is not finished, then what happens in the sense, the flow goes like this. So again, it keeps on disturbing about the disk. It checks the data whether it is ready or not. If it is ready, then it fetches the data, or it writes the data at the time for writing. So when it is done, if it is done, then it again continues the process. This is how the operation for this programmed I/O goes. So these are all the drawbacks of this programmed I/O. In programmed I/O, the CPU wastes time polling devices because it keeps on checking it, whether the services are needed by the devices or not. So it keeps on checking, and this checking is called as polling here. Another problem is that high priority devices are not checked until the CPU is finished with its current I/O task, which may have a very low priority. So the CPU will be addressing the low priority without caring about this higher priority, or without the awareness of the higher priority. So this is the drawback here. Programmed I/O is simple to implement, however, and so it has the advantages in some applications too. So another thing is interrupt-driven I/O. So in interrupt-driven I/O, the device requests the service through a special interrupt request line that goes directly to the CPU. With the interrupt-driven I/O, the CPU does not access a device until it needs servicing, and so it does not get caught up in busy waits. The advantage of this interrupt-driven is that it doesn't caught up in busy waits. Also, it doesn't waste time in polling. So this is the flowchart for this interrupt-driven I/O flowchart for a disk transfer. So say for a, if you see here, the process starts with this enter. So it issue the read or write request to disk, whether it may be read a data from the disk or write a data to the disk. And CPU doesn't care about this. It keeps on continuing its work. If you see here, it do other processing until the disk issues an interrupt. So it does other process until the disk issues an interrupt. So who want to give an interrupt? In the sense, the disk want to interrupt, or the disk should say, I am ready for read, or I am ready to write to the CPU. So it passes the message via an interrupt. So once it happens, it comes to the transfer data between the disk and memory. So interrupt causes the current processing to stop, and it transfer the data between the disk and the memory. So return from the interrupt, the normal processing resumes. So once it is done, if the normal process resumes, then it comes out of the process, otherwise the process continues. So this is how the I/O flowchart goes. The one thing is that the CPU just gives it just signals just signals the disk, and it keeps on continuing its own work without caring about this disk. Once the disk becomes free, the disk gives an interrupt to the CPU, saying that I am ready to read or I am ready to write. Then the CPU continues its process. Once it is done, then the CPU uh, continue its process once the transfer of data between the disk and the memory is finished. So this is about interrupt driven operation, and a special register which we discussed in the previous slide is the processor status register. So whether or not interrupts are accepted is generally determined by the state of the interrupt flag, which is part of the processor status register. So furthermore, in most systems, priorities are assigned to the interrupts either enforced by the processor or by a peripheral interrupt controller. At the top priority level in many systems, there is a non-maskable interrupt, that is NMI, which, as the name implies, cannot be disabled. The processor status register and the program counter are automatically pushed onto the stack, and the program counter is loaded with the address of the appropriate interrupt service routine. The processor status register is pushed onto the stack because it contains the interrupt flag, and the processor must disable interrupts for at least the duration of the first instruction of the interrupt service routine. Execution of the interrupt routine then begins. When the interrupt service routine finishes, execution of the interrupted program then resumes. So this is about the third communication methodology, that is the direct memory access. So what is the advantage of this direct memory access? Because each and every time we need to disturb this the CPU for this data transfer. So the advantage of this data memory access is that it doesn't we are in no need of the CPU. The data can be directly transferred between the disk and the memory without the help of the CPU. Let us see how. A DMA device can transfer data directly to and from this memory rather than using the CPU as an intermediary, and can thus improve the speed of communication over the bus. If you see here, the first the access will be like this. It has the data should be fetched from the disk to the CPU via the bus. Then from the CPU the data will be transferred to the memory. But if you use this DMA, with the help of this DMA controller, the data from the disk will be directly mapped to the memory. So DMA services are usually provided by a DMA controller, which is itself a specialized processor whose specialty is transferring the data directly to or from IO devices and memory. Most DMA controllers can also be programmed to make the memory to memory block moves. A DMA device thus takes over the job of the CPU during a transfer. In setting up the transfer, the CPU programs the DMA device with the starting address in main memory, the starting address in the device, and the length of the block to be transferred. So this is the DMA flowchart for a disk transfer. So the CPU sets up the DMA device and then signals the device to start the transfer. While the transfer is taking place, the CPU continues execution of another process. When the DMA transfer is completed, the device informs the CPU through an interrupt. A system that implements DMA thus also implements interrupts as well. If you see here, the CPU sets up the disk for the DMA transfer by it signals the device. Okay, so now the DMA device begins the transfer independent of the CPU. Okay, so now it goes like this. It sets up the disk for the DMA transfer, and now DMA takes the control. Now DMA device begins the transfer independent of the CPU, or it does the job of the CPU. So it goes like this. The DMA device interrupts CPU when finished. So now it has finished the job, and it interrupts while the CPU executes the another process. Okay. So now once the CPU is being signaled, then it continues to the other process. So likewise the process goes. And this is one important thing, that is the cycle stealing DMA. If the DMA device transfers a large block of data without relinquishing the bus, the CPU may become starved for instructions or data, and that its work is halted until the DMA transfer has completed. In order to alleviate this problem, DMA controllers usually have a cycle stealing mode. In cycle stealing DMA, the controller acquires the bus, transfers a single byte of word, and then relinquishes the bus. So this allows other devices, and in particular the CPU, to share the bus during DMA transfers also. Thank you.